working in energy storage are facing, as well as how they are trying to overcome those issues. So this will be a just gist, like how different researchers are working. So let me start with a motto that I can explain you better what is going on, because this is part of my work, what I worked in NTU, National Taiwan University of Taiwan, during my postdoc. So here I will show you that thing, and let me show you my outline. So my outline would be containing like introduction and lithium-ion battery as well as other battery technology. I think I don't have to explain much about battery technology, because our professor N.S. Satyanarayan has already discussed in details about battery technology. So I'll immediately move to anode-free batteries as well as lithium-sulfur battery anode-free batteries, and what are issues and how to overcome these issues. Especially, let us focus on roadmap and let us understand what exactly new battery groups are doing, and what exactly Tesla is focusing, and how they are improving their like battery technology, as well as what are the future scope, like what are the research we can focus for our future scope. Like just recent our past talk given by Dr. Dinesh Babu, that how they are developing the perovskite and what are the future scope in perovskites. So similarly, we can also focus like what are the battery technology and what can be the future scope in battery technology. Before that, let us discuss why actually we are focusing on energy storage or energy storage application, like generating more energy, because no doubt that the demand of energy is increasing day by day, not exponentially. So demand is increasing exponentially day by day. So as per our industrialization and other advanced technology and growing population, energy is quite comparatively low energy consumption is very high. So not it's not like that we don't have the energy resources, as we know that renewable energies are sufficient, but like even we have started depending on renewable energy apart from hydro, nuclear, coal or gas energies, and renewable energy applications is also growing. Like in 2020 we'll be having a better implementation of renewable energy, and as we know, like many there are like a lot of resources for the renewable energy. Like I don't have to discuss, like almost everyone know now that what are the sources of renewable energy. So from that, is it like why it's not still now not sufficient to generate all like energy and to be utilized by everyone, this energy, and to reach each the corner for everyone applications for this energy. This only generation is not a problem. The storage is also a problem, because when it is a sunny day only we can generate solar energy, or it's a windy day, then we can generate our wind energy. But what about the cloudy days or nights? So we have to think about potential energy storage devices. That's where it comes that batteries and supercapacitors applications, like generating a appropriate energy storage device. Because another point, like we never meet the demand and supply of energy, because we have to match that demand and supply. Then we have to really develop a very potential energy storage devices, and as well as the demand like energy applications like hybrid vehicles or smart electronics. Also we have to develop better energy applications. So for that, many research groups are focusing on fuel cells, batteries, and supercapacitors. In general, like as we know, fuel cells are energy conversion devices, battery and supercapacitor energy storage device. So it's we can focus, like we can capture the renewable energies and store the energy for our utilization whenever like we cannot generate the energy from renewable sources. That's why now it's an hot research area, how to develop a potential energy storage device as well as implement it as per our need. So as we know, the applications of energy storage devices, like especially the commercializations of the energy storage devices, because of our utilization, like in consumer electronics and industrial or commercial electronics, and also to develop the clean and sustainable energy, as well as for our automotive structure. As we know now, Ola is also going to give us like a proper very high energy density vehicles. So similarly, we have making the market of energy storage device more commercialized or more effective. So we have to focus on this battery technology and what are the advanced battery technology. Before that, let us discuss actually what are the old, like till now the battery technology has been discovered and and commercialized. Like as we know that lead acid battery, nickel cadmium battery, nickel metal hydride battery, or lithium ion battery. So here now we have almost lithium ion battery, sorry, now we have almost lithium ion battery, and we all are utilizing this battery because of its advantages like 3.6 volt and more than 2000 cycles with energy density of 150 to 200 watts per kg. And the most important factor that it don't have self discharge, like it's very less self discharge and no memory effect. And it's also quite less toxic than other batteries. Like here we can see that disadvantages in lead acid battery or sodium metal hydrate or nickel cadmium battery is like their potential window is very low. So most of people are still working on this lithium ion battery to develop its potential, to increase its potential as well as to increase its energy density. So in this area for developing the lithium ion batteries, more works has been carried out. So gradually I will show what are the different works has been carried out to improve this lithium ion battery. Before that, let's understand what is exactly energy density and power density and where the different kind of batteries stand. Like not only here the differences in potential window or in a memory effect or in expensive or anything, we have to also focus in the weight and size of the battery, as for the weight and size, how much the energy density and power density we are getting from the batteries, that is also a effective point. As well as cycle life and coulombic efficiency are very important parameters to focus on batteries technology. Here let me explain the mechanism what actually going in batteries. So I'll just give a gist. Like in battery, as we know, we are using the two electrodes like cathode and anode. Here in lithium ion battery, cathode is usually lithium based cathode like lithium cobalt oxides or lithium magnets or lithium iron phosphate. So similarly the electrolyte also lithium based like lithium like LiPF6 and some solvent, as well as then like anode materials like graphite or other anode materials like metal oxides and all. So this battery technology is especially depend on how we are using the cathode and anode and electrolyte, and that also governs the performance, electrochemical performance of the batteries, like its potential window or cycling stability. So choosing the nanomaterials for the battery is very important and a very important point where we can, so this in general this is the scheme for the battery charge and discharge. Like I think like no need to explain, already Professor Satyanarayan would have explained it. So I will just move what are the issues in lithium ion batteries. Like as we know, lithium ion batteries nowadays we are getting a lot of news like it battery catches fire and all. What exactly happening in that? So in that explanation I'll give, like why the battery is catching fire. Like in general, when we don't go deep into the research of these batteries, we don't understand what happened for the battery, why it is overcharged, why it is stolen, or how why it is not taking the charge for a long time. So these things like you now I will just picturize it and I can explain like why really it's happening like that. So in general we can see why lithium ion batteries like catch fire, or what exactly happen when like it is not safety. Like there is like dendrite growth, and lithium is very limited resources, so the dendrite growth affect the battery. then affect the battery, and there is a short circuit due to this dendrite growth, and it gets affected for this and like sorry, for the devices. And then what are the other issues apart from the lithium? As I mentioned, lithium is the cathode material for the lithium ion battery. So what are the other issues that that makes it disadvantage or bring the shortcoming for the lithium ion battery? Apart from cathode, the anode, like graphitic carbon, has also irreversibility and capacity loss during the charge discharge. That's why the battery has a limited lifespan. Like in general, if we see the battery, when we charge at the first few months, it is working very nice, and then devices are not charging, so not charging well, or it's not keeping charge. That's nothing but because of this capacity loss of the battery. Apart from that, when we use an anode material like metal oxides or other anode material, there is also a effect of volume expansion, which also affect the charge discharge of the batteries. As well as when we consider for the electrolytes face the problem like leakage or corrosion, and sometimes this also like there is other side reactions which degrade the quality of the battery. That's why apart from all this like cathode and anode and electrolyte problem, there is also a drawback, like lithium ion battery is quite expensive. So focusing on all this point, we have to really work on this battery to develop this battery technology to next level. So what we are looking for in this battery technology nowadays, like but till now our battery energy density is just 500 watt per kg. So the battery consortium has discussed like it has reached the limit of this battery energy density. So they but still now it's not sufficient to have power our energy devices what we are demanding in this advanced industrialization era. So we have to develop really battery with a very high power density and very high energy density. And as the cost is major factor, so we have to reduce the cost, and the safety issue is the major thing. As we know, we cannot afford this installation. I think we are facing the news like some fire in lab or some fire in industries and all. So those safety is the major issue what we have to focus nowadays. Apart from that, life cycle is much important factor for this battery, because like longer the battery, that longer will be our device life durability. So we have to focus in all these major point like energy density, cost, safe, as well as life cycle. So apart from that, I will say like lithium is a lithium ion battery has been commercialized, but we are going to face really a problem like abundance of availability of the electro material, because lithium is going to like lithium deposition is depleting. So we have to really focus on the availability of the electrode material, like and lightweight small compact devices are in demand. Like nowadays we are looking for flexible electronics, or like small biomedical devices with compatible size and all. So we have to also focus on lightweight small and compact devices. So what we can do, like really today's commercial batteries are not sufficient for our application. When we are talking about device, as I already mentioned, we have to focus all these parameters like electrode and electrolyte, separator, configuration, battery system, and packaging of the batteries. So when we consider all these things, the strategy are we should look into the different ion batteries. Like apart from sodium ion, we can look for the apart from lithium ion battery, we can look for the sodium ion, potassium ion, or magnesium, aluminum, zinc. So these are the very recent work like what people are focusing on this ion battery. As well as we can go for different cathode and anode based batteries, because like nanoscience has given us a huge avenue to explore the difference. So we can also focus on different anode and cathode battery materials, as well as different electrolyte of the battery. Like people are working in different electrolyte, like polymer electrolyte, or like sodium based silicate or aquasilicate, non-aquasilicate. So I will give a short view on this electrolyte also. So here it comes like as I mentioned that first we can focus on different ion batteries like lithium, sodium, potassium, calcium, magnesium, aluminum. But why these all, if these are very abundant in the earth, so why these batteries are really not commercialized, or what are the other issues has been faced by the researcher in lab, and why it's not being industrialized. So here if we see a comparison like lithium to sodium, so the potential window availability of sodium or aluminum is very high in earth abundance, but the energy density or charge storage by these materials are not comparable to lithium. So still there is a lot of parameters to be focused and to be developed by to improve the batteries, other ion batteries. Apart from that, like sodium ion battery, other anode material like graphite is not compatible for sodium ion battery, so battery, and sometimes the electrolyte is also not compatible for the sodium ion battery. So those kind of research are going on, like how to develop this sodium ion or magnesium ion battery. And most important thing, the electrolyte, they are focusing on highly concentrated electrolyte, or to reduce the water in the electrolyte. So they are trying to develop the electrolyte which can really give us a wide potential window, and also it can help us to increase the durability of the battery as keeps the coulombic efficiency, because when there is a less number of ions available in this electrolyte, that's also an important factor where we can focus like to develop the particular electrolyte. So what are the real things there? So let us see like what is the challenge, like what like exactly lib is facing. As I mentioned in my previous slide, like lib like really safety issue is a problem, like dendrite formation. And like, when the dendrite grows, like we call it lithium dendrite, so when the dendrite grows, there is a short circuit and it gets how the dendrite grows and what exactly it is. From this figure, I think we can understand. So here is an solid electrolyte interface. So what it do, like it prevents the dendrite formation. So when the lithium, when there is a continuous charge discharge process, so the lithium grows like a spine. So this solid electrolyte interface layer, it protects that dendrite to get connected to the other side electrode, and then it saves the electrode from the short circuit. But when there is a poor solid electrolyte layer interface, then or there is a fracture in solid electrolyte interface, so definitely the lithium dendrite causes the short circuit. And when there is a volume change of the electrode materials, like or like electrolyte consumption, then obviously the cyclic stability of the battery will reduce. And as well as this leakage also of the electrolyte, also a big parameter for like a disadvantage major challenges
Hello, ma'am. Hello. Hello, ma'am. Ma'am, can you hear me? Ah. Ma'am, you are muted, ma'am. Ma'am, kindly unmute yourself. Hello.
Yeah. Can you see it?
Yes, ma'am. There was some technical glitch.
Oh, I think net issue. So can you just help me where I missed the slide?
Just
What was the last slide? Can you just let me know?
just
Like, I don't know when the issue came. So is this the last slide?
I think after this one, somewhere here. Yes.
Okay. So I don't know when exactly technical issue happened. Sorry.
Okay, no issue. Please.
Okay. Thank you. So I think I was discussing like what are the challenges what the lithium ion batteries are having. So in the challenges I have discussed like solid electrolyte interface. So in solid electrolyte interface like this the solid electrolyte interface, if we face a fracture in solid electrolyte interface, or that is like lithium dendrite growth or volume change or electrolyte consumption is high or flammable and leakage, then the liquid electrolytes actually face such problems for the lithium ion batteries. So we can just go for a surface engineering process. So usually people researchers are searching for a compatible salts or we can say the additives actually. So in this additives, the solid may prepares a good solid electrolyte. So this good solid electrolyte can reduce the flammability as well as electrolyte consumption. So this when we go for an executive step for developing an artificial solid electrolyte, or when we reduce the less the fracture in solid electrolyte, it can definitely suppress the dendrite formation, and also it can reduce the electrolyte consumption or volume change in the electrode. So the major thing like to avoid the liquid electrolytes and disadvantage of liquid electrolyte, people are focusing on different types of electrolytes like inorganic solid electrolyte or liquid electrolyte or polymer electrolyte, or sometimes it is like composite electrolyte like mixing the solid electrolyte as well as gel electrolyte. So if we see the this such varieties of electrolyte, each electrolyte has its pros and cons consecutively. So here if we see inorganic solid electrolyte, even though it is a solid electrolyte with an high safety, but issues with this electrolyte is like poor cycling or poor performance. So instability happens in its interface. And when you go for liquid electrolyte, I already mentioned that excellent rate capability is found, but the stability or safety issue is very less because there is a problem of leakage and all. So majorly now in my future in current few decades, like people have focused in polymer electrolyte. So in the polymer electrolyte, we can really go for a flexible device, which is very important for nowadays for biomedical applications or for smart watches or anything. So that for that polymer electrolyte is important, but the issues with polymer electrolyte is like their poor mechanical stability, because when we can make it the flexible, so mechanical stability is a major point. So this face the mechanical stability as well as they face low ionic conductivity. So when like it is the next process has been thought of implementing the synergetic effect of both solid electrolyte as well as gel electrolyte to make a quasi solid electrolyte. So this composite electrolyte is very good in flexibility, multifunctional stability, safety as well as good ionic conductivity. But this composite electrolyte is also has a problem in fabricating the devices as well as for long-term contact issue or resistance. They have a higher resistance. So to avoid that, also people are focusing in developing this electrolyte with a different technique, like in mixing the electrolyte with the electrode material or increasing the conductivity. What can be really focused for the future research. So here I can give you as general facts like what exactly the issues with or the different type of electrolytes and where we can develop. Like if we focus on granites, like granites have very nice conductivity. Like I can just I'm just proud that I'm from Puducherry University, and one of our professor Murugan, he has first reported these granite structures. So this granites are really very nice for solid electrolyte batteries, but it has also the issues with stability with the air, and other issues like resistance and all. So this also has to be developed, like adding with other electrolytes, as well as when we go for Nassicon electrolytes, as granites are lithium based electrolytes, so Nassicon is also sodium based solid electrolyte. So that also face a lot of stability issue, as well as its potential window is less than the granites. So people are developing this Nashicon towards the improving the potential window and all. Similarly, when you focus on polymer electrolyte, as I mentioned in the previous slide, that polymer electrolyte is very nice, but it also face like potential window is low, because polymer gets degenerated, and stability as well as stability against lithium is has to be focused for polymer electrolyte. And when now we move to sulfur electrolyte, so sulfide based electrolyte has been used for sulfur lithium sulfur batteries. So in that, there, as we know, sulfur is not stable in air, so major issue is stability against the air. So and also stability against the lithium, as well as potential window. So as compared to the other electrolytes, this sulfur electrolytes face such issues which can be developed in further, and I'll be adding how to really develop the electrolytes. So before that, let us see what is the problem why lithium polymer electrolyte based batteries are not commercialized. So even though lithium polymer based batteries has high power density, no memory effect, low cost, robust and flexible, as we can develop the flexible device, and also it prevents the leakage there rather than liquid electrolyte, but it suffers points like suffering from aging effect or cost manufacturing, stores less power, as well as shorter lifespan. As I mentioned earlier, that polymer can degrade and it is not stable to air also. So this is the disadvantage like has to be overcome for the lithium polymer battery. So apart from that, where I have already said that lithium metal ion batteries are very much beneficial like other metal ion battery. So people have started focusing on lithium metal batteries. So what is real advantage of using lithium metal as anode? Because usually in half cell we use this lithium metal as a full battery. There we have found that the capacity is very high, and when we actually make a full cell, then capacity of the full cell reduces because of the specific mass. So to improve that specific capacity, people have used only the metal like lithium metal, or and also one interesting fact that when you use lithium metal battery, the amount of lithium will be sufficient rather than using the lithium ion battery, because from the lithium itself we can get the lithium ions, and it will be no there will be no insufficiency of the lithium metal. So people have focused on lithium metal batteries, but when we use lithium metal as anode, there are also many issues like dendrite lithium formation and low coulombic efficiency, because whenever the dendrite formation or other degradation of the anode happens, then coulombic efficiency reduces. And similarly, when the volume expansion happens, its lithium dendrite is very easy for formation, and it gives a short circuit. And most critical fact is when lithium metal we are using, the lithium is sufficient, but when with a gradual charge discharge, dead lithium is created. Well, what is the dead lithium? Dead lithium is nothing but inactive lithium. Like some of the lithium get charge discharge, and then it cannot return back to its original position. So those lithiums are really inactive, and again we faces insufficiency of the lithium in the lithium metal battery. So here I have given a short scale like solid state lithium ion battery. The energy density is like 800, rather than lithium ion battery in liquid state has to be increased more, and it has not yet reached 500 also. So other facts we can now also matter for the lithium metal battery is like electrolyte depletion, because in lithium metal, electrolyte is also an important factor here, and we have to also see. And the instability of ACI layer, as the lithium ion battery face a similar thing, instability of the ACI layer and electrolyte depletion. So here also in lithium metal battery, the same problem has been faced. So people really focusing on solid state lithium battery. So moving to this solid state lithium battery, here is the schematic where I can like we can see here in clear fact like how lithium metal battery can be helpful, or sodium metal battery can be helpful. So here we see when there is a utilization of the porous material as anode, and here we can see when utilization of the sodium metal or lithium metal. So the reaction is very clear, and it gives a good capacity when the solid electrolyte is also used. So this scheme can be really designed for the battery material. So the other thing, like when we move to lithium metal solid state batteries, like using a removing the liquid electrolyte and using here solid electrolyte, the cathode material will be same, that NMC or sodium cobalt oxides, or lithium cobalt oxides. And similar structure when you move to solid state lithium metal battery, like lithium metal will be used and solid state electrolyte will be used. Then lithium metal anode will be used for the anode, and cathode material will be same. So here we can find the higher energy density rather than using the graphite or silicon, because definitely the specific mass will be reduced, and the lithium specific capacity is also higher than graphite. So there will be a high capacity for when we design a solid state lithium metal battery cells. So here is a picturization like lithium dendrite growth. Here a small picture I have given. So I think one can understand what how the lithium gets dendrite growth. So when we just use the lithium metal as anode, so we can see that in the surface the lithium metal dendrite will be grown. Like the problems what we can face in lithium metal battery, when we have a lot of advantage of increasing the energy density or increasing the capacity, but still these are the issues what faced by the researcher, like there is a dendrite formation or low coulombic efficiency. Now what exactly will happen when this dendrite grows, this lithium grows in the lithium metal surface? It will just lead to short circuit of the battery, and dead lithium will created, as well as it will take a high surface. So coulombic efficiency will reduce because there will be a huge consumption of the lithium as well as electrolyte. So to focus that, we should it will just consequence in safety issue and short circuit. So focus that we have to develop, or we have to remove all these, like lithium metal batteries in solid state form also not giving a proper output what we are looking for. So but this lithium metal battery, this dendrite formation can be reduced by different technologies, by different approaches. Like here is the one of the approach, like as I mentioned, surface engineering. The surface engineering, like we can make a artificial solid electrolyte interface. So we can also like coat the material with some polymer, like when the polymer grows, like if there is no deposition of the polymer, we can see here the dendrite formation has happened. And like after many cycles of charge discharge, so when we give a polymer coating, so definitely the deposition is will not allow the polymer to grow, this lithium to grow, and the dendrite formation will be reduced. So this deposited, this when we just go for a coating of any polymer or any other material like gold, like sputtering of gold or anything on this lithium surface, so definitely there will be reduction of dendrite formation, as well as it can be form a flexible and high modulus electrode. And most important thing, like the side reaction, as I mentioned in my first slide, like many other side reactions happens, like people study with gas chromatography or HF production and all that. Those things will be reduced when we go for the electrode, this such type of approaches like coating or surface engineering of this electrode material. So similarly, when we saw like liquid electrolyte has lot of issues, so we can go for a sodium and other metal batteries. Or when we face like so in lithium ion battery, so we move to lithium metal batteries. So removing this anode material like graphite and other metal oxides with a lithium metal to increase our energy density and power density, but still we faced some of the few of the disadvantages like dendrite growth or this like dendrite growth or like volume expansion or low coulombic efficiency. So few researchers have thought this anode free lithium batteries. So it is really surprising how can it become like anode free. So but when we think like when we are not going to take any anode and just we are going to develop this battery. So is it possible, like even when I also heard it first time, so I was very surprised. So how can it be possible we don't take an anode and the battery is complete? Because from the time I have started electrochemistry, we are always thinking like okay, a positive electrode and negative electrode that can make a battery. So what is the technology and how people are making this anode free battery, and how exactly they are trying to make a solid state anode free battery? So here we can see like people have developed like anode free battery. So cathode material will be nearly same. It may be NMC or it may be lithium ion cobalt oxides, or like what is the best cathode material we'll take to our as per our application. So anode will be just nothing like copper foil, and no other neither metal or nor graphite or any other oxide. So it will be just simple copper layer, like copper edge current collector for the anode free battery. So when you go for anode free, what exactly the advantages we get theoretically? In theoretically we can just imagine like when you go for a anode free battery, so definitely the size of the batteries or energy storage device will reduce. Why? Because no anode material, so definitely the specific mass is reducing, so we'll get the enough free battery energy density, very high energy density will get. And like here we can see, like as I mentioned, the energy density what we have reached for lithium ion battery is not sufficient. So here we can see when there is anode free battery, the energy density can be around more than like 1200 watt per liter. So it's almost 60% higher to the current existing lithium ion battery. So when we think of this, it's really very really commercialize anode free batteries, because anode free battery, when you think of this or try to make in lab, it may be easy, but when you go for a mass production, there may be a lot of challenges what we have to face. So can we really commercialize, or if we want to really make it work like anode free battery without any anode and same electrolyte, same cathode, then what are the issues we are going to face, or what kind of problem we are going to face, and how to tackle those problems? So if we study this anode free battery, so here we'll see there are irreversible phenomenon, like the same phenomenon like dendrite growth and dead lithium, or like reduction of electrolyte, overconsumption of electrolyte, limited lithium source, or cathode degradation or oxidation of the electrolyte. This I think, like as I explained, like all this effect in lithium ion batteries as well as lithium metal batteries, I think these are all the similar facts for the anode free battery. But when we are not using anode, then where these effects are coming? So these effects will be starting like after few cycles of charge discharge. After the few cycles of charge discharge, the current collector where we are using the copper is not only the copper, because the lithium will be deposited on this layer, and that same thing will start the dendrite growth. And the same thing, the lithium, whatever source, like already we have reduced the lithium, but the lithium source will generate the dead lithium. So there will be a very insufficient of the lithium, which will ultimately reduce our coulombic efficiency. So the anode free battery, almost like I have not shown any of the work, but if I like for the thing, I will say like efficiency is very low, like sometimes we just get 20%, or like till now we have developed till 50. So we want like really very high coulombic efficiency. So there are a lot of work is going on to increase that efficiency. Apart from that, like there is very limited source of lithium, as we are not using any anode. So lithium source is only the cathode. So it is a big challenge, like how the lithium source should be maintained well in the system, as well as the oxidation of the electrolyte and the cathode degradation, because now the total pressure is on cathode, so cathode degradation happens, and the side reactions are also as similar as lithium and batteries. So it our challenges has increased in this anode free battery. So here I have mentioned few of the factors, what are the real challenges in the anode free battery, like ACI fracture, corrosion, volume change. Yeah, here is the point, like corrosion, what exactly happening, because of the anode free current collector will be like empty copper. So the corrosion of the current collector is very visible in the anode free battery, as well as on this copper layer there will be accumulation of the dead lithium. And the similar things like leakage and like poor interface connection or interfacial stability and gas evolution will be happening in anode free lithium ion batteries. So I think now I think like we can suggest from my previous slides, like it is better to go for a anode free solid state batteries, because like will at least will prevent it will prevent from electrolyte consumption, leakage, or volume change, or the safety problem will be solved. So anode free solid electrolyte, again it is really challenging to develop a anode free solid electrolyte battery, because when you move for a solid electrolyte anode free battery, then the challenges again are added for solid electrolyte, as well as the anode free challenges. So what are the things what we can really think of to make the anode free solid electrolyte batteries? Like we can think of alternative cell design, or we can think to structure the current collector, because as I mentioned, we are using the empty current collector like copper coil for developing the anode free battery. So we can really develop structure the current collector so that it can host the lithium for in a better way to have a durability, or a long term charge discharge, as well as we can use certain electrolyte which will be very efficient for our electrode. So electrolyte can be the performance of the electrolyte can be developed by adding few additives to the electrolyte, and then we can also focus on optimizing the electrolyte solvent, like as in the electrolyte we are using solvent like EC and DC. So we can optimize this solvent in different ways, and the concentration of salt we can increase, because in the salt concentration, the electrolyte salt concentration also plays an important role to our limited source of lithium in our system. So this one of the other fact can be like we can design some new protocol or some new electrolyte or interface the engineering. So what is this new term, that interface engineering? So I'll be discussing in few things, like as in the previous slide I told, one surface engineering can be done, like coating the coating the lithium metal so that we can avoid the dendrite formation. Similarly, we can also work for coating the current collector to develop to prevent the other effective. So such kind of work also such kind of works are mentioned in this interface engineering. So majorly what issues are focused in NF3 are like dead lithium, dendrite formation, unnuclear solid electrolyte formation, electrolyte decomposition, solution structure of the electrolyte or interfacial. But how to know what exactly happened in our system. Suppose I just fabricated a battery, then I just put for charge discharge and I don't get anything, like my battery is not working. So what are the techniques where I can know what exactly happened in my battery, and what how can I tackle this problem? So nowadays people are using very advanced technologies like characterization technologies to understand actually what happened in battery, and what can be done for the its development. Like in situ studies has been done, like imaging techniques has been used, like optical microscope or scanning electron microscope, or institute same or tem apart from that, people are also doing like theoretical studies, like in structuring the liquid electrolytes or brain red growth formation or interfacial. Such things also can be calculated in a theoretical way to imagine how the battery will be going to perform, focusing on spectroscopy techniques, in situ spectroscopy techniques, like when there is the lithiation and dilithiation, they continuously do the Raman spectroscopy or ITR study or XRD, so that they can analyze how the structure of the electromaterial is changing during the charge discharge. Most interesting studies, like few groups are specifically focusing on NMR or EQCM to know the lithiation and dilithiation during the charge discharge cycling of the battery, so that they can understand how the dendrite is formed and to what extent the dendrite is formed, and this so that they can know how much the coating should be done, or what the additive electrolyte can be used, or how can they prevent the current collector from the dead lithium or this dendrite formation. So overall, from all these studies, the goal is like we'll make a metal deposition on the current collector, or we'll increase the we go for a high energy density in a low cost and safety of the battery. So for all this system, as I mentioned, there are a lot of parameters or a lot of characterization technique where we can get to know what are our issues and how can we change it. So here I have just given a summarize from a very interesting review, that how people are analyzing the battery technology, and how people in advanced research work, how they are focusing on different issues and how they're trying to solve. Like here, if I just say it's specifically, like as I explained this dendrite growth or ACI layer thickness, how to measure and how to know how much layer, or MRI techniques. And similarly, when we go for like lithium concentration in electrolyte, or we go for like what if the gas evolution has happened. So they are studying this the evolution of gases, like during charge discharge, like H2 HF or H2S or other side products has been formed. So they are specifically studying this by gas mass chromatography. So these are the very recent techniques what people are using to understand the advanced battery technology, and to understand the electrode change or the concentration or the gases formed during the charge discharge. So this is, I think, like whoever working in deep battery work, so they can focus, they can go for this review or literature where they will understand really how to characterize our battery, and how to understand that what exactly issue has happened during our charge discharge. So as I explained, moving towards the anode free battery, and moving towards the solid electrolyte battery is one of the new challenge and one of the new advanced technology in the battery technology what we can focus. Similarly, here I want to say also, apart from lithium ion battery or lithium metal battery, people are also focusing on lithium sulfur batteries, because the sulfur is very abundant and eco-friendly. And the very important fact in this sulfur lithium sulfur battery is like specific capacity will be very high rather to the lithium ion battery. And here what we can do, like we can use the lithium and sulfur system, like anode material like lithium anode and sulfur based cathode for this system. And definitely this charge, this energy density of the lithium sulfur system will be very high, like almost 5 times that of the lithium ion battery. So but the issues, like what really practically hindered the sulfur lithium sulfur battery performance, is low conductivity of the sulfur and large volume expansion of Li2S electrodes, cathode materials, and then instability of the sulfur. As we know, the sulfur is various polymer structures, so it gives a different, it gives in different stages of charging and discharging, different unstable materials, so which doesn't allow the battery for proper cycling. So apart from that, there is also dendrite formation as well as dead lithium formation during the charge discharge. So this they also suffer from polysulfide formation, which makes the loss of sulfur. So the coulombic efficiency again reduced when there is reduction of sulfur in the system. So here we can see when we use the lithium anode battery, there will be like dendrites in lithium anode, and when we use the sulfur based cathode, there will the sulfur content is less, as well as the charge discharge will reduce. But interestingly, when we use the lithium free anode, like some carbon or silicon, the dendrite formation will be less, as well as when we used
Ma'am, you are not audible, ma'am. Ma'am? Hello. Ma'am, you are not audible, ma'am.
There will be a dense structure of lithium
Hello,
as well as sulfur. So
right. This live channel. Hello, ma'am.
yeah,
Ma'am, you can switch off your video, ma'am. I think
clear. Video. I can switch up my video. You are saying that, right?
you can consider that. Maybe your network is not stable. You can switch off your video.
Yeah. Just a moment.
Or shall I stop, ma'am?
Yeah. Can you just do it?
Yeah, I can. Okay,
Yeah.
please.
Okay. Thank you. Okay.
Please
So
proceed.
even though when we use the lithium sulfur sulfur based cathode, as I said, that there is a problem in stability of the sulfur, and the sulfur content reduced when there is a huge number of sulfur formation. So we can think of lithium sulfur cathode materials, because no doubt it gives a high specific capacity and long cycle, because this Li2S cathode will be a dense structure, as well as it will contain a sufficient amount of lithium and sulfur. And the major factor is, like, we have to adjust the lithium and sulfur balance in this system, like lithium sulfur system. We have to adjust the electrolyte as well as electrode material, so that the sulfur loading will be sufficient for the system. So especially when for a better battery performance, like around specific capacity 800, and the cycling stability, like we want around 1000. So we have to keep the high loading of Li2S, like more than 5 mg per cm square for the electromaterial, and the best performance is achieved in the low ES, like around 3 microliter per mg. So what are the limitations when we use Li2S system? Like as we know, the limitations in Li2S system is low conductivity, low ionic conductivity and electroconductivity, as well as when we see Li2S in a bulk Li2S, it is electrochemically inert. So with the electrochemical inert Li2S is not going to give us proper charge discharge or well potential. So we have to really reduce the think of how to make the Li2S electrochemically active. So apart from that, the activation energy of Li2S is very high. So even though we can activate the Li2S, but we have to spend a lot of potential to activate this. So there should be other way to recover from the oxidation of the polysulfide, or for reduce the generation of the polysulfides, because when the polysulfides generates, there is very high resistance or slow charge transfer. So we can also the major problem in Li2S system is like it's very moisture sensitive. So every time we have to work in globe box, so we have to think of that problem also. Apart from that, Li2S crystallization, it's easily crystallized to antifluoride structure, which also reduces the performance of Li2S. So delithiation of Li2S is more challenging, and it affects in life cycle of the Li2S batteries. So when we think of strategies to recover from all these issues, so we can go for electrochemical activation of Li2S. Especially this is done by changing the Li2S, bulk Li2S to nanomaterials. Like when we make it to nanoscale, then Li2S become conductive. And we can also focus on structural engineering and synthesis alteration. Like when we synthesize Li2S in different process, then the conductivity also increases, or it become like more electrochemically active. Like in general, the Li2S synthesis is done by ball milling, because it is very easy and we can get moisture free. We can synthesize this in a moisture free environment, like just in we can generate it in glow box and then go for ball milling. And also the doping of different metals or chalcogen can help the Li2S to increase its activation energy. Like as I mentioned that it need a high activation energy, so doping of other material will reduce its activation energy. So few of researchers, they have also focused on this, like especially very renowned battery group like BJ Wang in Taiwan, NTUST, as well as Manthiram, one of our Indian Professor Manthiram is working in Texas University on this Li2S system, and they have reported a lot of research work like on this basis, like how to really activate the Li2S as cathode material for Li2S system. And they are also working on solid electrolyte anode free battery, so to develop the lithium sulfur solid electrolyte battery. And the other ways are like we can also use redox mediators like or catalysts to with the Li2S, so that its conductivity will be increased, as well as activation energy also reduce. So apart from the electrode, we can also develop the electrolyte in this Li2S system. Like usually in Li2S we use lithium LPS for as electrolyte. So in this LPS system we can add some other like additives to increase this, or we can just coat the PO or other polymer for the electrode to improve the performance. Like here we can see the different strategies in this scheme. Like Li2S cathode, we can also put carbon coating or polymer composite or the redox mediator, so that our focus will be like we can develop the lithium metal battery with low dendrite, as well as enhanced safety, low cost and high energy density. So as I here will be like summarizing the what I said, like anode free solid state lithium sulfur battery. Here if I summarize, as we know, there will be no lithium, so it is safe and assured. It is less weight also, high energy density and free from liquid electrolyte. But the challenges are low lithium sources, electrolyte, as well as the deposition of lithium on anode, and low coulombic efficiency, rapid capacity of fading or dendrite formation. So when we go to lithium anode free solid electrolyte, so as we know the solid electrolyte, there will be wettability issue, like electrode and electrolyte interaction will be reduced, and their reversibility also will be issue. as well as active material. Utilization of active material will be reduced, because when it is liquid electrolyte, it gets well interacted with the electromaterial, but in solid electrolyte the movement will be less, and the electrolyte material cannot interact properly. So these are the major issues when we go for anode free solid electrolyte batteries. And why exactly this interaction issue happens? Because the resistance of the solid electrolyte is very high, and as compared to that, the dendrite growth will be also effect more in this case, and then it will be affecting the like our anode free solid electrolyte battery. So for achieving this all these advantage and overcoming these issues, so we have to work in these possible approaches. Like we can reduce the size of Li2s, so that our surface area will be enhanced, and lithium diffusion will be also easily happen, so that our charge transfer will be also faster, and the distance will be reduced considerably. We can also generate Li2s cathode with a different material like porous host, or we can add some carbon like vulcanized carbon, or some sp2 carbon to improve the electronic conductivity and reduce the sulfur trapping in the Li2s. Then we can go for also for binding the sulfur with some polymers like sulfurized polyacronyl, or some other polymer, or especially we do like we use the electrolyte to bind with the cathode material, so that there will be sufficient electrolyte during the charge discharge, as well as there will be sufficient electrolyte in the system. So what we do, we just add the electrolyte in a proper ratio, where we can also increase the conductivity of the cathode, as well as we can help the system to be in sufficient electrolyte. So here apart from that, we can also make the artificial interlayers in the electrolytes. Like when you use the separator, so we can just go for coating of the separator with some polymer, so that the dendrites will be reduced, the formation of dendrite will be reduced, or dendrite like uh, the ACI layer will be not destroyed if we just coat some other layer on the on that surface, or we generate some artificial ACI. So that will be also helpful. And apart above that, we can also think like how to reduce the polysulfide formation. Like if the how to control the polysulfide formation, then we can use some of the other solvating agents, or some of the additive in the electrolyte, so that the polysulfide will be reduced, and then it will increase the density of the electrolyte. So as I mentioned, the activation of Li2s is most important, and that will also suppress all the issues what I have discussed here. So we should plan how to do the how to change this form, and it will definitely work better when you use such kind of cathode material, or such kind of approaches we use to overcome the issues in lithium sulfur anode free batteries. So here, just in schematic, in a short form, we can understand really what we have to do in a anode free solid state lithium sulfur battery. Like we have to adjust the LPS and Li2s system. Like as I mentioned, like we can use electrolyte in a cathode material, so that the balance will be maintained, the E by S ratio balance will be maintained. And also the when we balance the Li2s content, then lithium ionic conductivity and electronic conductivity is also balanced, and then lithium and sulfur ratio also will be balanced. Apart from that, we can also develop use the carbon. So when we use a sufficient amount of carbon, the conductivity will be also balanced, and then the performance of the cathode will be also balanced. Then the if Li2s it will stop also for Li2s degradation, or sulfur trap, or polysulfide formation. So similarly, when I go for the anode free current collector, so if I can go for coating of metal, or coating of some polymer, so that that on the current collector, when I coat the other material, it can trap the lithium in a proper way, and also prevent the dead lithium formation in on the surface of the current collector. So this scheme, if I just keep in mind and go for a work in anode free solid state lithium sulfur battery, then definitely I can help I can focus on developing a better lithium and solid state lithium sulfur battery. So my strategy is like we can just focus on using this lithium sulfur cathode with carbon, and we can focus on thickness or crack of ACS, and also amount of lithium in anode free battery, and then focus on solid electrolyte and anode free. As I just said, the mixing of this LPS in Li2S is a major factor. So this factor can be governed like how much amount of lithium Li2S we are using, or how much amount of carbon we are using, or how much amount of LPS we are using to really develop the cathode. So why exactly the amount of these materials are necessary to be used in a proper ratio, so that the best cathode should be developed. Because when you go for anode, there is no anode and the total strain is in cathode, so developing a potential cathode is much more important. So because as few of the factor is like ionic and electronic conductivity, so here the ionic and electric conductivity will be balanced by using a proper balance of Li2S with carbon. Apart from that, when we just mix some of the electrolyte with Li2S and carbon, then the conductivity of the cathode also increase. It also suppress the subtle effect, as well as it there will be a sufficient electrolyte in the system. So this is the fact why we should really balance this Li2S and LPS system. It's really not that easy, because we have to try and try, like many protocols has to be developed to get a proper ratio of Li2S carbon as well as LPS system. Because when it is a solid electrolyte, there are these challenges are really big challenges, where like we have to see for like how the electrodes will be working and how the performance will be coming. And as I mentioned, this is solid electrolyte, so interaction will be very less and the resistance will be very high. So the when we just synthesized the material and then go for a charge discharge, the battery just so no charge discharge or just short circuit. So it's quite difficult and challenging process for developing this solid state anode free sulfur based battery. So one of the strategy, as I mentioned, that when we dope other transition metals to lithium sulfide system, then the activation energy of the Li2S reduces. As you'll see, this group from Professor Manthira tellurium in this Li2S system, so that the lithium anode free will be developed, and the capacity also is very nice, and life cycle is also very high. So the sulfur system is also working nice, because this tellurium is captured, and it doesn't allow those Li2S to degrade faster. As I said already, that major factor for developing the anode free is the current collector. How we are like we can do interface engineering to develop the current collector, or how we can use the current collector in a proper way to collect the to really tackle the lack of lithium or shortage of lithium, or how to tackle the charge discharge without hampering the dead lithium, without we should not get the dead lithium or dendrite formation. So what exactly can be done with current collector to make it anode free? So many people, like different strategies they use, like when they use the current collector as copper, they have changed it to copper form, so that it can capture a lot of lithium when it comes for charge discharge, and then the anode will be developed when it is a anode free battery. So anode will be formed when the charge discharge happens in a copper form. Apart from that, people are using nickel foam as current collector, and with a ink coated on the nickel foam, as well as they are also going for different pattern of coating on the current collector, and then or else electrode deposition by, like they are depositing some of the polymer by electrode deposition method, or by electro spinning method. They are depositing some of the polymer on the current collector. And also the interesting and easy way, what I feel, like we can go for sputtering, like gold sputtering, or some of the silver, or different sputtering can help the current collector to avoid the formation of alloy during the charge discharge. And also it can help for a better performance when during the charge discharge, and avoid the formation of lithium dendrite or dead lithium on the current collector. So these are the interesting points where we can really manipulate or tune the current collector to get a better performing anode free battery. And to play with this anode free battery, we have to really focus on electrode material, how to develop a better cathode material, electrolyte, as well as this current collector. So this part of work is very interesting, like developing different current collector, and then tuning the current collector performances by tuning its interface engineering or surface engineering. So it's one of the interesting fact. So apart from that, apart from the fact, like we have to focus on cathode, electrolyte, and anode, we should also focus on packaging of the battery, because when you ask for commercialization, like what I asked in my first slide, like when we really make commercialize for the anode free battery. So when you go for commercialization of the anode free battery, so different types of packaging also will question our commercialization. So as you know, there's various types of batteries in market, and packaging types. So this anode free battery can also be packaged in pouch cell to increase the energy density, surface area and energy density, as well as they are also packed in different forms. I think till now we have not developed that much anode free battery, because this is growing technology. So we have to think of different other ways how to pack these batteries to get a better performance, because anode free liquid battery has its own challenges, but anode free solid batteries are now approaching. So we have to think how we can make this solid batteries, and how can we can make it flexible solid state batteries. So I think this is the summary of what are exactly different types of batteries, and different type of new advanced technologies, and researcher during developing the anode free battery, or lithium sulfur battery, or lithium metal battery. So as we can see, each battery has its own pros and cons. So we can really focus on developing different type of battery, as well as how to work for those battery, and how to progress in our research. So I will leave this question on the audience, to our participants, like what kind of battery really we want to develop, or what future we are looking for, our future need of electronics appliances, or what batteries we really want for our future. So I leave this thing, and then I will really encourage all everyone to really go for a this such kind of research work, and really think of what next we can do, because in this energy technology, future is still awaiting. So here I will acknowledge the AICIT MBIT for inviting me, and Utkal University, as well as my financial for Rusha, and HOD coordinator of FDP program, and all the members of FDP, as well as Rusha coordinator, and all the participants. Thank you for joining.
Thank you, ma'am. Thank you. It was a wonderful session.
Thank you.
May I now ask the participants, if you have any queries, you can ask. Either you can unmute and talk, or you can put in the chat window. If there is some queries from the participant side, you can put in the chat window, or you can unmute and talk also. participants can put their queries in the chat window. Is my voice not audible?
No, sir, you are audible.
If you have any queries, you please put in the chat window. I think ma'am has finished her lecture. So thank you, others. It was a very nice session. We know. Ma'am, there is a question in the chat box by Dr. Saravanan. Why there is variation in holding of volt or battery backup more in lithium than other compounds? Do you like to answer them?
Sarvanan, actually, I'm not clear about your question, but I think you are trying to understand why the backup is more in lithium, right? Or
yes, ma'am. Yes, ma'am.
Like in lithium and battery, why there is more backup?
Yes, ma'am.
Okay. Do you mean by memory effect, or backup means what you are asking?
Mostly they will be used for the lithium for the several purposes comparatively other compounds. That's why I'm asking. Several studies report also said that mostly they will be used for the lithium based battery. Why there is more and more research?
Backup means what you are asking, like to
capacity. It means higher capacity, or it may be it can able to store for.
Okay, why lithium has higher capacity?
Yes, ma'am. Yes, ma'am.
Okay, because lithium is lightest metal, right? As I mentioned, like people are also trying to develop sodium ion battery, potassium ion battery. So it depends on its active mass. So as lithium has very low mass, so its capacity is very high. So when I said like we can go for anode free battery, so the capacity the mass will be reduced, right? So the when mass is reduced, definitely the specific capacity will be increased. Okay.
Okay.
So you can, if you want to know, like I can tell you some other time, like the basics, how to calculate the specific capacity, and how exactly for the like different compounds we can calculate the specific capacity.
It's enough. It is enough, ma'am. Okay, fine. Thank you.
Okay.
Thank you, Saravanan. If there is any other question, we can go for. Otherwise, we can wind up for today. Vinod, would you like to add something?
Sir, no, sir. Actually, so I want to thank Himadri ma'am for giving an excellent talk. So, thank you, ma'am. So, for giving a useful session in so regarding anode-free batteries. So, thank you, ma'am, once again.
Thank you, sir. Thank you,
ma'am.
Sir.
Yes, ma'am. Thank you. We'll get back to you, ma'am. I think we'll be meeting again on Friday.
Yeah.
Okay, we are eager to know about the recycling and reusing of batteries.
Okay, sure. See you.
So we will meet again, ma'am. Thanks for the wonderful session. So I think we can wind up for today, ma'am. I think participants has one more questions here. Thank you, ma'am.
Thank you. Yeah. Good luck to everyone. Bye-bye.
Participants, we can join tomorrow morning by 9:45. You can join 5 minutes earlier. Please fill the feedback form